So we were discussing what we were discussing. We were discussing optoelectronic junction devices, right? So we have photodiode, light emitting diode, photovoltaic devices, right? So these are the three main classification of optoelectronic junction devices. So what is photodiode? Advait, what is photodiode? What is photodiode? Advait.
Photodiode converts
Hmm.
electrical energy, light energy in electrical energy.
Light energy is to electrical energy. So photodiode is a optoelectronic junction devices. So that will convert light energy to electrical energy. Okay. So we have to tell it is optoelectronic device junction devices. That also we have to say. Okay. So this was a simple. Okay, this is simple, and this is a like actual photodiode. And next one was the light emitting diode. So photodiode we already discussed. Now we are going to discuss light emitting diode. Okay, so this is actually one light emitting diode. This looks like this, and this is the symbol. Let me explain that how a light emitting diode can be constructed. Okay, and how it will operate. So light emitting diode is also a optoelectronic PN junction device, but which converts biasing electrical energy to light energy. Okay, so this is the symbol. Either you can represent like this. Okay, so this is a diode, and it is emitting lights. Okay, so that's why the arrow mark like this. You can represent like this or this way also. Both are light emitting diodes. Simple. And how it will work. Okay, so this I told it is a PN junction diode, right? So this is a PN junction, P and N. The top portion we have a conducting material, so through that we are connected to a what, battery. So you can see that, right? So is it forward biased or reverse biased? So is it forward biased or reverse biased?
Forward biased.
Forward bias, right? So we have certain mandatory requirements. Okay, so for light emitting diode to work. So what are they? Let's see. First important thing is the energy gap. That is EG. What is energy gap? It is a gap, energy difference between the valence band and the conduction band of the semiconductor used to make this PN junction of this LED should be greater than 1.8 electron volt. 1.8 electron volt. Okay, that is the first condition. So why it should be greater than 1.8 electron volt, I will explain. Then second important point is high concentration doping and forward bias. This is the second important requirement or mandatory requirement. First is energy gap. EG should be greater than the semiconductor by which this LED is going to make. The first condition is its energy gap should be greater than 1.8 electron volt. And second thing is the doping concentration should be high. What it means? Its doping concentration is very high, should be high. What is the meaning, Aditya? What is the meaning? High doping concentration. So what is mean by doping and what do you mean by high doping concentration, Aditya?
So, what do you
Hmm.
mean by doping and high doping?
Yes,
Okay.
I'm, I'm asking that. What is doping? What is doping, Niranjana?
Sir, adding impurities.
Yes, adding impurities, right? So that is the main thing, right? When we are going to make a like semiconductor or PN junction, N type or P type, it is extrinsic semiconductor, right? For making an extrinsic semiconductor, N type or P type, we need to add impurities, right? Pentavalent or trivalent, right? So that process is called what? Doping. So high concentration doping means the amount of impurity addition should be high. So then what will happen if if I'm increasing the doping? What will be the benefit? We will get more number of electrons in N region and we will get more number of holes in the P region. So for that purpose, we are we need to use high concentration doping. Okay, why we require that much of free electrons and free holes in the case of LED? So that we will explain. That I will explain. Okay, so these are the two conditions, right? So clear? What is this 1.8 electron volt and what is this high concentration doping? Forward bias, you know. So these are the conditions. So any doubt on this?
No.
No. Okay. Now just think about, okay, the PN junction diode. So when we are making a PN junction diode, what will happen? You know that, right? What will happen? Let me draw that. So this, suppose this is a PN junction diode. Okay. So single crystal, I will be doping P-type material here. Okay. Then N-type material here. Okay. This is P-type. This is N-type. So what will happen? First thing, diffusion, right? So after diffusion, we will get ions only at the junction, and these junctions we will call it as what? What we will call? What we will call this junction? What is the name of this junction?
Depletion region.
Depletion region, right? So these are holes, and what will be here? It will be positive and electrons, right? So this is the way of formation. Here only negative ions and positive ions. This is the way of we will get what? PN junction is formed. So initially diffusion current will be there. So it will increase, then it will after some time the diffusion current reduces, and what current starts? The current due to the minority charges. Okay, so that current we will call it as drift current. First it was diffusion, then after the diffusion current reduce, then this like drift current due to the minority charges happens. Why this drift current is happening, that I already explained. I think you know that, right? Because this minority carriers, here it is what? Electrons, here it is holes. Because of this high electric field, these electrons, minority electrons, will get attracted towards the end region, and here from here the minority holes will move to the P region. So that is drift current. So that is minority current. So diffusion current and drift current will happen. So after some time, both diffusion current and drift current, or the minority current and majority current, will be equal. Okay, then this PN junction will be in equilibrium. Right? That we know. Then we what we will do, what we studied, we will apply forward bias. When we connected a forward bias, what happens? What happens? Tell me. I am connecting this is forward bias. What happens? Forward current will happen, right? So because this is positive, this is negative. So here there are a lot of electrons. So this positive negative charges will repel this majority carriers, and this majority carriers will cross this barrier. Okay, right? So then we will get a forward current. So electrons will be moving from this to this. Current will be in the opposite direction, I forward. That we know, right? Current is from positive terminal, but electrons will move from negative terminal. So always the conventional current direction is opposite to what electron current. So electron will be moving from here to this junction, then it comes to this positive terminal. But current is in this direction. Conventional current direction is opposite to electron. That we know. Now, just to think, see, from this end region, lot of electrons are crossing this junction and reaching this what P junction, portion of that PN junction, right? Then is there any chance to recombination? Right? There is the chance of recombination also, right? So there will be lot of suppose thousand of electrons are coming to this P region. In that, some 100 electrons can recombine with this holes. Balance 900 will move to this battery. There is a chance of recombination. So when an electron recombine with a hole, what will happen? The energy will emit. The energy will emit. So this junction diode can emit certain kind of energy out of it. Okay. How it is happening? Because a free electron, how it is coming actually, it is attaining certain amount of energy from this battery, right? So due to that energy only, this free electrons from this n region is moving towards the p region. So since it is recombining with some hole, some energy will lose. It will lose the energy, and that energy will radiate out, and that will in the form of EM wave. Okay, then suppose if that EM wave frequency is in the visible spectrum range, we already know, right? Visible spectrum, we studied in the fifth chapter, not like the electromagnetic waves. So if this EM wave frequency is within the visible spectrum, then we will get, or we can see it. So this will be a visible light. This is the process happening in light emitting diode. Understood? This electric energy through this biasing. Okay? Electric energy through this biasing will convert into visible light. How it is happening? It is emitting the energy that it is acquired from the battery after recombination with the hole. So that energy we are getting in the form of EM wave. Then if that EM wave frequency is the emitted EM wave frequency from the junction, if it is equal to the, or if it is within the spectrum of visible light, we will able to see that light. So that is the working principle of light emitting diode. Is it clear? Clear? Advait, Shiva, only
Sir,
thing, yes, tell me.
sir, ഒന്നുകൂടി പറയോ?
Yes. So what we have to do, like what is the requirement? We need to produce what?
Energy,
Light. Yes.
ആ, ഒന്നുമില്ല.
We need to produce light from the electrical energy to this PN junction. So when we are connecting this PN junction with this battery, this forward bias. So electrons will move from this N junction or N portion of the PN towards this what? Towards the P region. So what will happen? Suppose there are 1,000 number of electrons are moving towards this P junction. Some of, not all, some approximately let it take its 100 electrons will recombine with the holes which are available in the P region. Due to that recombination, this 100 electrons will lose energy. That energy will be radiated in the form of EM wave. Understood?
Yes, sir.
That if that frequency of the emitted wave, if it is in the visible spectrum, you know, right? What is the range of frequency? So in that spectrum, if that we getting this emitted energy or emitted radiation, then we can see it is as a visible light. So we will get a light output. Clear?
Yes, sir.
Yes. Ranjana,
Yes, sir.
clear. Ranju, Advait,
Yeah.
clear? Advait, see, listen. If I'm
Yes,
not
sir.
getting the response, please switch on your camera.
Yes.
Aditya,
Yes, sir. Clear.
clear, right? Okay. Now, now you just think about the requirements. I told that we need a 1.8 electron volt. It should be greater than 1.8 electron volt. Why? And what is the requirement of high concentration? So first I will explain why we require high concentration doping. Why we require high concentration doping. Just you think that, okay, 100 people are walking around through a road, like along a road. റോഡിലൂടെ നടന്നു പോവാണ് 100 ആൾക്കാർ. Okay, suppose there are 2 or 3 pits, കുഴികളുണ്ട്. Okay, suppose they are moving with a very slow speed, that the chances of falling in the pit is less or more. കൂടുതലാണോ അത് കുറവാണോ?
Koro.
Yes.
കുറവാണ് അല്ലെ? If they are moving, suppose only 100 people are moving, that will be not 100 people. Can I rub it? I'm just rubbing it. Suppose only 10 people are walking along a road. There are certain pits and they're moving very slowly. So the chances of falling on the pit is less, right? Right. Suppose there are 1,000 or 10,000 people are moving. That means the Terakku Kudi. So the chances of falling on the pit is high or low? High, right?
High.
Same thing. That's why. So we have to, for getting the light output, the energy we require to emit, right? So for that, what need to happen? We need to happen more recombination of electrons and holes. So that's why we are giving high concentration doping. So if I am increasing the concentration of doping means more free electrons and more holes. So the chances of recombination will be high and we will get the light or energy will get emit. More energy will get emit. So we'll get the light out. Clear? Why we require high concentration doping?
Yes, sir.
Clear, right? Now think about why we require 1.8 electron volt. Second mandatory requirement. Why we require? So we know that the frequency of electromagnetic wave is equal to energy divided by h. What is h? Planck's constant, right? So the frequency of this emitted light or the emitted, we don't know it is light, it is not visible light, right? The frequency of the EM wave that is emitting due to the recombination, okay, depends on what? The energy and h. H is a constant. So this frequency is proportional to the energy. So if you want to get within the spectrum, if this frequency, so there are electromagnetic spectrum, right? EM wave. So if you want to get the visible spectrum, so it is the visible spectrum. The frequency, if you want to get within this spectrum, this energy should be equal to 1.8 volt. Then only this we will get the frequency within this spectrum. Clear? Very simple. You have to correlate with this equation because
Sir,
the freq.
one more
Yes.
question.
See, we know the equation F is equal to what? Energy divided by Planck's constant. So H is a constant, right? So what is this frequency? Frequency of this emitting EM wave. We don't know it is light. We have to make it as a visible light. Okay? We have to make this the emitting energy or the EM wave, the radiation, what? Light or visible light, right? നമുക്കത് ലൈറ്റ് വിസിബിൾ ആയിട്ട് കാണണം. സോ അതിനെന്താ ഒരു സെർട്ടൈൻ ഫ്രീക്വൻസിയിൽ ആയിരിക്കണം അത് എമിറ്റ് ചെയ്യേണ്ടത്. എന്നാൽ മാത്രമേ ലെറ്റ് ഇറ്റ് ബി എഫ് ബി, ഐ എം ടേക്കിംഗ് വിസിബിൾ ലൈറ്റിന്റെ ഫ്രീക്വൻസി അറ്റ് എഫ് ബി. എഫ് ബി എന്നുള്ള ഫ്രീക്വൻസിയിലെ ഇ എം വേവ് റേഡിയേറ്റ് ചെയ്താൽ മാത്രമേ നമുക്കത് വിസിബിൾ ആയിട്ട് കാണാൻ പറ്റുള്ളൂ. ഇറ്റ് വിൽ ബി വിസിബിൾ ലൈറ്റ്. ഓക്കെ, അപ്പൊ നമുക്ക് എന്താ ഈ എഫ് ഇ എന്നുള്ള ഫ്രീക്വൻസിയിൽ നമുക്ക് ജനറേറ്റ് ചെയ്യണം ദി റേഡിയേഷൻ. സോ ഫോർ ദാറ്റ് we know the equation F is equal to this frequency of this emitted wave depends on the energy. Here what is the energy? Energy is emitted what? The recombination. Here the energy is what? എങ്ങനെ എനർജി ഉണ്ടാവണേ? കണ്ടക്ഷൻ ഇലക്ട്രോണിന് വാലൻസ് ബാൻഡ് നിന്ന് കണ്ടക്ഷൻ ബാൻഡിലേക്ക് പോകുമ്പോഴാണ് എനർജി കിട്ടുന്നത് അല്ലെ? സോ ദാറ്റ് ഈസ് ഈക്വൽ ടു വാട്ട്? ഇ ജി, orbital energy gap, right? Conduction band. So this is the energy that electrons is getting. So that is equal to Eg, energy gap or orbital energy gap. So this is Eg. Okay, those frequency depends in this case the energy gap of the semiconductor used. So that energy gap should be greater than 1.8 electron volt. For what? To get the frequency of the emitted light or the emitted radiation within the visible spectrum of Fe. Let it be Fe. Clear?
Yes, sir.
Yes, sir.
Clear, right? So these are the two mandatory requirements. So why this required? So that also we want to understand. That is very, very important. Okay? Clear? Now you got what is the mandate? What is light emitting diode? You understood. What is the mandatory requirement? Two mandatory requirement. 1.8 electron volt energy. Why? High concentration doping and forward bias. Why? You got the answer. Right? Now it is very simple. What I explained is same thing on written here. So the intensity of the emitted light, we are getting the light as output, right? So this will increases with the forward bias. See, high energy gap, which should be visible spectrum. Eg should be greater than what? 1.8. The faster recombination of holes and electrons is giving the EM wave. To make this EM wave to this visible spectrum, we have to make this Eg greater than 1.8 electron volt. 1.8 electron volt കൂടുതലാണെങ്കിൽ മാത്രമേ radiate ചെയ്യുന്ന frequency should be in the visible spectrum or visible light. Okay, that's all. So this is the VI characteristics: voltage, then forward bias current. Okay, so we will get the different color of light because the frequency of each light will be vary. Okay, that it is shown here, different colors, VI characteristics, simple thing. Now just think, what is the advantages of LED over conventional incandescent lamp? What is incandescent lamp? What do you mean by incandescent lamp? Srilashmi, what do you mean by incandescent lamp? Who knows? What is incandescent lamp? പഴയ ബൾബ്സ് കണ്ടിട്ടുണ്ടോ? ഫിലമെന്റ് ഒക്കെ ഉള്ള ഉള്ളില് കണ്ടിട്ടുണ്ടോ?
Yes, sir. Tungsten.
ടങ്സ്റ്റൺ ഫിലമെന്റ് ഉള്ള ലൈറ്റ് കണ്ടിട്ടുണ്ടോ? കാണാൻ ചാൻസ് ഇല്ല കുറെ ആൾക്കാർ ഇപ്പോഴും. അപ്പൊ അതിൽ ഇപ്പൊ എല്ലാം LED ലൈറ്റ് ആയി അല്ലേ? സോ ടങ്സ്റ്റൺ ഫിലമെന്റ് ഉള്ള ലൈറ്റ്സ് ഉണ്ട്. അതായത് ലൈക്ക് ദിസ്, ഒരു ബൾബ് ആണെങ്കിൽ ഇങ്ങനെ ആയിരിക്കും, ഇതിന്റെ ഉള്ളില് ഒരു ഫിലമെന്റ് ഒക്കെ വെച്ചിട്ട്. ദിസ് ഈസ് ഇൻകാൻഡസന്റ് ലാംപ്സ്. സോ ഇവിടെ എന്താ ചെയ്യുന്ന, ലൈറ്റ് ഈസ് പ്രൊഡ്യൂസ്ഡ് ഡ്യൂ ടു ഹീറ്റിംഗ് ഓഫ് ദിസ് ഫിലമെന്റ്. സോ heating effect on it is comes in play in incandescent lamp. Okay, so here it is heating effect. Here what, the recombination of electron and holes emits light. Okay, so then that is the difference between LED and incandescent. So what is the advantage? So the operational voltage required for operating the LED is very less. Okay, so if you change your incandescent lamps with LED lights, so you can reduce your what, electricity bill, because the operational voltage and power consumption of LED is very less. Second, long life. Easily you can switch on and off, because for incandescent lamp you have to switch on, that filament need to get heat up. Okay, so there is a delay, little bit delay, but in the case of LED immediately less heat will be produced, because it is not working on the basis of heat. It's not working on the basis of heat, but incandescent lamp is working based on the heating effect. So less heat will be produced. So these are the advantages of LED over conventional incandescent lamp. Now let's see some of the application. Can you tell some of the applications you have seen in your daily life? Just think. Seven segment LED display. Have you ever seen this? 7-segment LED display. Any go?
No, sir.
No. Now you tell me. Did you see this anywhere? കണ്ടിട്ടില്ല എവിടെ?
ഇത് കണ്ടിട്ടില്ല.
So this is made up of LED. Okay, this each segment is an LED. 1, 2, 3, 4, 5, 6, 7. So that's why it is 7 segment. Using this we can make numbers up to 9, right? So this is an application, very very important application of LED. 7 segment LED display. What else? In optical communication. Okay, then as indicator lamp. What it means? Indicator lamp with electronic devices. Have you seen this? Have you seen this application in your daily life? You will say no, but when I saw the picture, easily you can understand. See this? This is a what? Receiver, right? of your cable TV. So this is a kind of indication. So as an indicator lamp, on off indication, on off indication can be done with the help of light emitting diode. With the help of light emitting diode, on off. Okay. So also some critical things like if it is red light, normally it will be off. So that light, different colors of light LEDs can also be used as an indicator lamp. So these are the some of the applications of in LED light. And another one is infrared LED. So that is different type of LED which is used as burglar alarm. So it will use as a combination of LED light from the LED will pass. Okay, here we will use a photodiode. Okay, so light energy will incident. So photodiode will give some kind of current. So that will be detected. Okay. Then suppose someone is passing through this. So what will happen? This light will block. So there will not be any light falls on this photodiode. So this current will cut. So this can indicate with some alarm. So this will be used as a burglar alarm. Someone is thief is crossing. We can use it. So infrared LEDs are used in burglar. So these are the some of the important applications of what LED lights emitting that we can study. Okay, so light emitting diode is over. Next is photovoltaic device. Photovoltaic device, example solar cell. So what is a photovoltaic cell? Photodiode gives light to energy, it is converting to electrical current, right? Electric LED, it is converts electrical energy or electrical biasing voltage into what? Light output. Photovoltaic is a PN junction, optoelectronic PN junction, which converts light energy to voltage. You know the solar cell, right? Solar, what it is doing? It is producing what? It is producing electrical energy from light energy. Electrical energy from light energy. Now you will be thinking that what is the difference between photodiode and photovoltaic cell? Right? Both are producing what? Electrical energy from light. Then what is the difference? What is the difference? So after I'm explaining this photovoltaic device, you should able to identify what is the difference. Okay, so let me explain what is photovoltaic device. So it will use certain amount of voltage. Let's see. So this is a symbol. Okay, because we are getting voltage, so that's why battery is simple from the light. Okay, so this is it. Working of a photovoltaic device. Here also there are certain mandatory requirements. Energy gap should be between 1 to 1.8 electron volt. Then only we can get the minimum voltage. If this energy gap between the conduction band and the this one conduction band and the valence band, the energy gap should be within the range. Then only we can produce certain amount of voltage from this solar cell. So that is the first condition. Second condition is the doping concentration. It should be n layer. The thickness of the n layer should be approximately approximately 0.3 micrometer, and for the p layer it should be 300 micrometer. That means 1000 times. The thickness of the p layer should be 1000 times greater than the n layer thickness. So these are the two conditions. And also third one is high optical observation or absorption. So we have to choose the material to make this PN junction of a solar cell. These three conditions you have to make. Okay. Now you see how it will work. I will explain. Okay. You see, this is N. This is P region. Bottom it is nothing but it's a metallic contact. The top is also a metallic contact. So light will be falling on this. this will be converted into voltage. How it will be converted into voltage? That we need to understand, right? Let's see. Now we are considering a PN junction. Let me take it. Take a PN junction. So this is a PN junction, right? Now you just think, okay, certain light is falling on this junction. Certain lights are falling on this junction, sunlight. I am not connected to anything. There is no biasing, nothing is there. Just you think what the process will happen inside this PN junction when the light falls on this junction. Think it. Think yourself. When the light falls on this PN junction, what will happen? There is no biasing. External voltage ഒന്നും connect ചെയ്തിട്ടില്ല. Simple one PN junction. Okay? Just light is falling on the junction. What will happen? You think? Think and tell me. First thing you know, right? From the light, there is covalent bond, right? There is covalent bond, right? Inside this, there is no free electrons, but there is electrons within the covalent bond. So when the light hits on this junction, the electrons within this covalent bond in this region will get certain amount of photon light energy. So that then if the electron get light energy, what will happen? What will happen? Shivam, what will happen?
It will get excited.
Yeah, it will get excited. It will get excited. So suppose I'm taking one electrons here. Okay. So it gets excited and it is reaching here. This is the electron. So here there will be a hole. So actually here there is a covalent bond within this ion. Okay. So due to this light energy, this electron from this covalent breaks the covalent bond and it gets excited and it is reaching here. Understood? So there will be a hole produced here, electrons here. Now what will happen? Think. Positive ions here, negative ions here. What will happen? Immediately these electrons will swept to this, right? Immediately these electrons will swept to the right. So electrons will produce. Already there are electrons, but those are in equilibrium, so there will not be much potential. But these electrons will swept. So similarly, lot of electrons will be produced due to this light excitation. All will be swept to this what end region. So lot of electrons here, external electrons, and also lot of holes will be produced in this P region. Then what will happen? Electrons is negative potential, lot of positive charge here. So if you connected a voltmeter across this junction, we will get certain voltage, certain readings in this voltmeter. Yes or no? Yes or no? Kito? Kito. Okay? So we will get certain voltage. So we are getting voltage as output. What is input? Light. So light is the input, but we are getting the voltage as output. That's why we call it as what? Photovoltaic cell. But you just think about, now you just think about photodiode. Photodiode also converting light to electricity. But what is the difference? In photodiode, if you want to operate, we have to bias it. Here there is no biasing required, right? Here there is no biasing required. But in photodiode, we have to provide biasing. What kind of biasing? Renju, in photodiode, what kind of biasing we have to give? Renju,
Yes,
in photodiode, what
forward,
kind of biasing we have to give? Forward bias or reverse bias?
forward,
Ah, reverse bias. ഫോർവേഡ് ബയാസ് ചെയ്ത് എന്ത് സംഭവിക്കും? ഫോട്ടോഡയോഡിന്റെ ജംഗ്ഷൻ ഡിപ്ലീഷൻ കുറയും. കുറഞ്ഞു കഴിഞ്ഞാൽ എന്താ? ലൈറ്റ് അതിനകത്ത് ഹിറ്റ് ചെയ്യുന്ന ഏരിയ കുറഞ്ഞു കഴിഞ്ഞാൽ നമുക്ക് കിട്ടുമോ? ദ ഇന്റൻസിറ്റിക്ക്. അത് മാത്രമല്ല, ഫോർവേഡ് ബയാസ് ചെയ്ത് കഴിഞ്ഞാൽ എന്താ? ഫോർവേഡ് കറന്റ് ഉണ്ടാവും ബിക്കോസ് ഓഫ് ബയാസ്. അപ്പൊ ജംഗ്ഷൻ ഡയോഡിലൂടെ പ്രൊഡ്യൂസ് ചെയ്യുന്ന കറന്റ് വിൽ നോട്ട് ബി പ്രൊപ്പോർഷണൽ ടു ദ ലൈറ്റ് ഇൻസിഡന്റ് ഓൺ ദി ജംഗ്ഷൻ. Okay, for that we have to reverse bias the photodiode. That is the reason why we are operating photodiode in reverse bias. Okay, so that is the difference. Are you able to correlate the difference? What is photodiode? What is this one, photovoltaic cell? In photodiode, we required a biasing. That is a reverse biasing. What is biasing? External voltage we have to apply to operate it. But here, we don't want to give any kind of biasing. In what? In here, solar cell or photovoltaic cell. We will get the voltage as an output. Clear? So no?
yes,
Okay. Shiva, Srilashmi,
Yes, sir.
yes, sir.
clear, right? Any doubt? No doubt. So just we will see some of the applications.
സാറേ 6 മണി ഞാൻ പിക്കോട്ടെ.
കഴിഞ്ഞു.
ആ
These are some of the application of solar cell. Solar panels to store charge in batteries. So these are solar cells. This is solar panel. So from that solar panel, light energy we can convert into battery voltage. That voltage we can save or store in a battery. So this is the first application. Second one, solar wristwatches. So these are solar panels. Due to this solar energy, this will operate. Third one, spacecraft. Very, very important. So these are solar panels. This satellites are getting energy from this solar. Okay. So this is another application. These are the three important applications of photovoltaic cell or solar. Solar cell is a kind of photovoltaic cell. Okay. It's an example, very, very important examples of example of photovoltaic cell is solar cell. Okay, so these are the applications. So I think we have finished it for LED photodiode, LED photovoltaic cell.